Okay, so what I want to start with is to say, why do we want to simulate? That Paul gave a little introduction to that, and then what would be the best approach to doing this? So first of all, we don't just start to simulate because it's nice, but we have an experiment, we have a problem, we analyze the problem, and we want to find a solution to that. So we look at the experiment, we try to get out what are the key parameters, and how can we formulate some sort of mathematical model taking these parameters and predicting what we're interested in as a property. Then we run a simulation with this set of experimental parameters. We compare it to the experiment and we say, does it actually reproduce our experiment or not? If not, then okay, go back to start. We did something terribly wrong with our parameters or the model. Then we reevaluate this and we try to improve the model. If yes, the question is, are we now confident with the model? Maybe one successful attempt is not quite enough. So we do this a couple of times until we say, okay, now we believe in our model, and we are at this stage finished with what I would call the model development. Once we have that, we can then start to use the model, which is the more interesting part, probably, where we just simulate with a modified set of parameters with respect to here, and we just see, is it interesting? If yes, if no, then okay, we change the parameters. If yes, then we actually do the experiment, and so on. Now, just to say, in an ideal world, from what I said before, there has to be the experimentalist and the modeler, and ideally they're in the same building, they work very closely together. The modeler tells the experimentalist, hey, I've done this, I need this type of parameters, can you do the experiment for me and I can validate? Even better if it is the same guy doing both, because then he doesn't have to talk, but he just does both things. However, this is extremely seldom to find persons who can actually perform both things at the same time. Okay, that's the ideal world. Now to the real world. Most often, they are not in the same building, they are quite far apart, and communication is somewhat interrupted. Now, even worse, this guy is just sitting all by himself in his house. He doesn't have an experimentalist to talk with, and this is something that happens way too often and is actually quite scary, I think. The second thing I want to show is what type of simulation approaches we have and where we can maybe use them for ceramics. So if we start very macroscopic with a piece of ceramic, we can really treat this as a continuum. This is just a material and we don't care what is inside. If we zoom in further, we get a microstructure. If we zoom in further still, we get the atomic structure. I don't have a picture here of the electronic structure, but we can zoom in further still. So we see that we have quite a long distribution along a length scale, going from an angstrom to the meter, so 10 orders of magnitude, that we can cover with different simulation approaches. To do macroscopic modeling, we use something like finite element methods, etc., where we can go to the really large length scales. Here we would use what is known as mesoscale modeling methods, where we treat particles or grains as the primary building blocks. And finally, we have molecular mechanics methods, where atoms are what we're dealing with. And finally, we can do quantum mechanical methods, where we actually look at electrons and what they do in the material. All of these methods are also going to allow us to go to a very specific time scale. With the quantum mechanical methods, we can go up to a picosecond. It's not very long with respect to most material processes. Molecular mechanics allows us to go up to nano, sometimes microsecond range. It's still not very long. And the higher we go up in this scale, the longer we can actually run our simulations. This shows that there is a big variety of methods, and we better choose the right one, because I don't want to simulate a macroscopic piece of ceramic using quantum mechanics would probably take me 1,000,000 of years, so not very interesting. In IP Nanoker, there have been quite a lot of simulation, research and simulation. We have started with the very big, so we have done finite element simulations for the case of SPS and for thermal and residual stress analysis in sprayed coatings. Then there were some fluid dynamic simulations for the spray processes, some thermokinetic modeling, which is more analytical modeling. We had particle interaction modeling, optical mean field models, so this is more the mesoscale. And finally, we had atomistic simulation. And the ones that are red here now is what we're going to hear about later today. What I'd like to do now is to actually position all of these methods with respect to a ceramic production cycle. Since the goal of this modeling is to actually make better ceramics, or to give us hints on how to do better ceramics in the laboratory, it is quite important to see, okay, where do we target our research? The first one, segregation. Okay, segregation, it's hard to pinpoint it exactly because it happens in the powder production if we put our dopant in at that stage. Also during processing, we can add dopant there, or then later it's going to act during sintering. Methods that we use to calculate segregation, and it's me going into more detail on that later, is empirical potential models where we just can evaluate the energies of different atomic configurations. So we have arrangement of atoms, we see, okay, this one is more favorable than another one. We can therefore say where the dopant is going to be. We get interfacial energies, energies to put in dopant into our material. We can get equilibrium shapes and concentration of dopants at the interface. This is quite useful to understand where are the dopants, what do they do, and then have some clues for experiment on how to better use them. Colloidal stability, I would probably put it here. One could argue it's also during powder production if you want to keep the stuff in suspension. Where we use the DLVO theory, we've seen it already mentioned this week, where interaction potentials between different particles are calculated as a function of their environment they're in. And Paul is going to go into more detail on that later. And we can predict stability requirements, so in other words, processing conditions we need, and the processing time that we have, so the time these suspensions are actually stable. Thermal spraying is, for me, a shaping process. I'm not a specialist at all, so I hope I'm not stepping on anyone's toes here with my classification. Computational fluid dynamics are used to model here the combustion chamber, then the nozzle, the jet, and the deposition. And this is useful to actually optimize the geometry of these things and the conditions of the powder. So the particle size, is the stuff going to melt or not? And how is it going to be deposited on the substrate? For sintering, we had finite element modeling to actually understand what happens in the SPS, since that's quite unknown. And so simulations were done on the SPS chamber, and Sauce is going to explain that better than me, I hope, I think. And actually with this, we can understand what is the stress distribution, temperature distribution in this SPS, and to actually understand how does it sinter, and then based on that optimize the sintering cycles. Thermokinetic modeling has been done by Frank Kern in Stuttgart, where he took dilatometry results and he fitted them to analytical reaction schemes to actually get out what happens exactly, or not what happens, but how to optimize two-stage sintering cycles. We're not going to hear about that, but if you're interested in this sort of modeling, then maybe go and talk to Frank. Yeah, okay, there's a poster outside. For sintering as well, we've done some atomistic simulations, a combination of two methods, metadynamics and Monte Carlo methods, to calculate energy barriers for diffusion, then diffusion traces or trajectories, and finally diffusion coefficients. And this is useful if we want to understand actually how does an atom get from A to B, how long is it going to take, and maybe better understand what actually happens during sintering. On the applications, we had some applications of optical mean field models. Carlos Pecheroman explained a bit on that yesterday, where we tried to predict the transparency of a microstructure as a function of its size, its texture, maybe the porosity and second phase, and other possibilities we have seen, for example, the inclusion of phonon dispersion in the optical models. And this is really useful if you want to predict microstructure target values that we should get to in sintering. If we can say this grain size is going to give us the best transparency, then the experimentalist can do without too many different attempts actually get to the right grain size. What we have also done is to try to evaluate laser performance, and this is going to be the topic of my afternoon talk, based on dopant segregation. So we want to look at what proportion of dopants is segregated, what is actually the rate of dopants that sit in the grain, and want, based on that, actually get an understanding of this quite new class of ceramic lasers, which I was at a laser ceramic conference, and I had to know that actually these guys don't know it at all what is a ceramic. They treat it as a single crystal, which is not quite true. So we actually want to understand this and see what are the possibilities we have with this kind of material and what are the issues we're going to run into in their development. So in more detail, we're going to see these talks here. You have to program yourself. And, okay, what did Paul put into his slides here? This looks like the simulation team as we were doing a workshop in Stuttgart. And thank you for your attention.